Momentum conservation is also complicated. You can have a very high momentum object collide with a planet, and you get a very messy intermediate state. But sometime later, the planet and the comet all recombine, and you have exactly the same total momentum initially as you have afterward, no matter what collision it is, no matter how complicated. Angular momentum conservation is probably most readily demonstrated by the way a gyroscope behaves. While it's spinning in free space, it'll always preserve its angular momentum. You have to exert a torque, which is a combination of force and distance, to change its angular momentum. And you know how gyroscopes have a funny behavior when you start playing with them, which is because you're fighting angular momentum conservation. You try to move the position or orientation of the gyroscope. And you can see it here with the spinning professor holding the two dumbbells, who then pulls the dumbbells in. To conserve angular momentum, you have to increase the velocity of spin, the angular velocity. In fact, it goes quadratically. If you have this distance, you need 4 times as much spin. And so, in fact, you see this rapid spin up, and it's sort of impressive, and ice skaters know this, and it's just the conservation of angular momentum. But in some sense, the most important symmetry of all, and the thing that really launched modern physics, and I don't have the time to go into it in detail, is the principle of that the laws of motion are the same in any state of motion. And in fact, the theorem we get from that is that if you have an object just moving uniformly through space, empty space, if you don't do anything to it, if you don't exert a force on it, it will continue to move in a straight line at the same velocity forever. This was a very difficult concept. The ancient Greeks were not able to get this concept because they lived in a friction-dominated world. And as long as you live in a friction-dominated world, the equation you're going to get is, in some sense, force equals mass times velocity. You know, something's big and massive. To get it to move, I have to apply a force. If I stop applying the force, it stops. If you have wagon carts with wheels that don't have the best bearings, and I know they didn't back then, then you stop pushing, it stops. You should go to Pompeii sometime and look at the ancient Roman streets of a busy city. And what you'll see, often the streets coming downhill to an intersection, those streets are built of massive rocks that the Romans nicely put together and flattened out. But as you approach the intersection, you'll see these deep wagon ruts. Those wagon ruts are these heavy carts that actually start rolling, starting to stop at that point, and the friction has dug these ruts into the pavement. It's quite impressive. You see it graphically at Pompeii. So they had potholes in Rome too. But basically the notion of something continuing to move by itself without a force applied to it was something they couldn't grasp. And it was so difficult that even when we had Copernicus's theory that put in the late 1500s, where the sun was at the center, and Kepler had gone in and understood that the motion was not circular. I mean, there was almost a religion for 2,000 years about the circle. Religion believed it had to be circles, those orbits, and they weren't. They were ellipses with the sun at a focus. And Kepler got the exact laws of motion, and still people did not understand the law of inertia. And it really took Galileo, Descartes, and others to understand that it wasn't the pushing of the planet in its orbit that was relevant. It was what was causing it to move away from a straight line. And once you figured that out, you could get to Newton. Newton's first law, which distills what people had figured out in the previous 100 years, is that an object remains in uniform motion unless acted upon by a force. And what that really means is all states of motion are equivalent. If there are no forces around, the object will continue to move in the same state of uniform motion. And if you're riding with it, you don't notice anything different about the physical world than somebody who's staying at home not moving. That what really happens is the force changes the velocity. And so it's not velocity that appears here, it's acceleration. And then the force that 1 exerts on 2 is minus the force 2 exerts on 1 is actually, and it's tricky to see it, but it's actually due to the translational invariance of the laws of physics. So these symmetries are already encoded into Newton's laws. Here's translational invariance, and actually this equation is rotationally invariant because that force is a vector pointing one way and the acceleration points the same way as the force. And I can just rotate the system and the equation stays the same. So all of those symmetries of space and time are encoded into these laws. And then Newton took the big step of telling us what the force really is. See, he has this equation that almost means nothing until you tell me what the force is. It means that force causes change in velocity, not position. But the force, he figured out, is the inverse square law force, the universal law of gravitation. And then he invented the subject of calculus. So he could solve the mathematical problem of what is the solution to this equation when this is the force. Starting with something with some initial velocity, how does it move? And he proved it was an ellipse, and he proved Kepler's laws were correct. That's enormous progress, and this is the beginning of the scientific modern era. So now, this question of, see, the symmetries are really buried in here. It's a little hard to see them. This symmetry, the fact that this is related to the equivalence of all states of motion is subtle, but it is. The fact that this is related to the conservation of momentum is subtle. You have to prove momentum conservation from this rule. And Einstein really turned it on its head. And he said, let's think directly about the symmetries. So